have a variable named a, and you're trying to get the memory address of it. Now keep in mind, this is the integer variable a. A is not a pointer by itself, okay? This is saying that a is just a regular old integer variable. So how do you get where that memory address is stored? C. The ampersand operator will give you the memory address of whatever variable you're looking at. Ampersand operator will tell you, will return the memory address of where it lives, even though, no matter what variable. So, let's go over why a is not the value. A. So, asterisk in front of a variable, if you guys remember, is the dereference operator. Dereference means that, hey, this thing I'm putting the asterisk in front of, I guarantee you it's a pointer. I promise you it's a pointer. And since it's a pointer, can you please get me the value of what you're pointing at? Not the address of what you're pointing at, the actual value of what you're pointing at. The reason why it's not correct here is because of two reasons. One, a is not a pointer. A is just a regular integer. There's a difference between a being a pointer and an integer. And that asterisk also doesn't return you the memory address in this case. It would return you the value of what is stored at a. Okay, so it's wrong for those reasons. B is not correct because that's literally just get me the value of a. It's not anything other than get me whatever is stored at a. If a was a pointer, sure, that would get you the memory address of the value of a. However, a is not a pointer. A is just a regular integer. Then you have answer D, and there is no such syntax. There's no function built into C++ to get you the memory address of a, so that wouldn't be correct anyway. Any questions on that? Okay. Question number 3. Which of the following gives the memory address of a variable pointed to by pointer a? So, it's saying that a is a pointer now. And because it's a pointer, we know that it stores a memory address. Okay? And what is it storing the memory address of? Of whatever variable it's pointing to, right? So the case in this answer is just A. It's storing the memory address of a variable pointed to by pointed A. We know that by itself a pointer stores memory addresses, so A will return back a memory address. What does the asterisk in front of A return again? It returns the value of what is stored at that memory address, not the actual data. Just remember there's a distinction between the value and the memory address, right? You guys remember this little spreadsheet I made? There's the address, variable, the value. Right? And so I had my memory addresses. And then I had my variable A. I'm going to call a variable foo. And I'm going to create a variable A. And I'm going to put foo actually down here. And foo holds the number 42. And A is a pointer. So int pointer A. And this guy is an int foo. And this guy holds the value 0x. So when you have the pointer variable A, this is the value that it's currently storing. It's storing a pointer to int foo. If I want to get the value of what's stored here, if I want to get this value that's stored at this memory address, I put an asterisk in front of my variable, my pointer, and it will go to that memory address. So I'll go down to here, and they say, okay, I'm here at this memory address. Get me the value of what's stored there. And it gives me back 42. That's what the asterisk does. So if I go back here, and I ask for the value stored at the address pointed to by pointer A, the answer is I put an asterisk here. answer A, which is the variable name lowercase a, if I just do that, that just gives me the memory address. That's the answer to the previous question. There's also no such function called val in C++. And what would the ampersand in front of a return? In our example, what if I put an ampersand in front of a, what does that return? If I have my expression here, here are the three possibilities for a. So I have a. What is the result of a? That's the answer, right? I do asterisk a. Result of a is 42. But the ampersand of a, what is here?
0x06.
Wait, the ampersand of a? If this is the memory address of where the variable a lives. Where does the variable a live on my example to the left? 0x01. So look at these three. These are three ways you can interact with variables. Okay, you can use these on any variable. However, some of these will cause a crash. Specifically, the second one here can cause a crash if you're not using it appropriately. It can cause a crash because if this thing, the way this works is, if that thing wasn't pointing to anything, and you say, get me the value of what you're pointing at, the first thing it tries to do is say, okay, cool, I'm going to go ahead and grab your memory address that you're pointing to. Looks like nothing's there. And then says, okay, I guess I'll get the value of that. And that behavior is undefined. And it would crash because it doesn't know where to go. It has no memory address. So this only works for things that are pointers. Can anyone tell me what that would return? Do the operation from inside out. This is asking for the memory address of the value of what's stored at A. Okay? Break it down. Do this part first.
42.
What is that? 42. Because you know that that's here. It's pointing to this value.
And then you get the memory address of 42.
0x06, right? Does that make sense? See, those things are interchangeable. You can combine them as well. So because these three, the standalone variable name, the asterisk in front of a variable, and the ampersand all do different things, you just have to think about these as, give me the value of A. This is get the value of what's pointed by A. So these are what those three operations do. So going back to our homework, this right here, answer D, gives us the memory address of pointer A, which is not the value of what's stored at the address. Okay. I know there's a lot of like syntax getting thrown around here, but this is again a good reason why the more you do it, the more you'll understand. It's something that's not you're going to get like the very first time. So, okay. Question number 5. Which of the following is a proper keyword or function to allocate memory in C++? You guys use this?
Yes.
It would be new. Malloc is the C way. Malloc is a way to, it's the old C style method of allocating memory. Malloc basically just takes a request for how much memory you want, and will return you back a section of memory that fits that request. Create does not exist in C++, neither does value. Okay. All right. Question number 6, the opposite. Oops, I did not mean to highlight that. This one. Free is the old C style method for storing memory, but in C++ you're going to be using delete. So every new has to have a matching delete associated with it. Question number 7. I asked you guys for an int pointer called Pikachu. So how do you declare something that's an int pointer? So I want it to be called Pikachu, so I know that's a variable name, and I know it's an int. So to declare a pointer, you have to put the asterisk in there. It doesn't matter which side you put it on, but one of these two sides you put it on, okay? How do you dereference Pikachu? This is just using the terminology here. Dereferencing means I want to get the value of what's stored at this address, so I do asterisk Pikachu. Okay. Questions on that? Okay, this is a logic exercise. If the value of Bulbasaur is 21 and the address of Bulbasaur is 400, what is the address? What is the value of Charmander and Pikachu? Okay. This is just using the operators that we had figured out earlier. Bulbasaur has the value of 21 and the address of 400. Go back to my example. This is where Bulbasaur. Bulbasaur has a value of 21. And I have Charmander and Pikachu as two variables. So I'm setting Charmander equal to Bulbasaur directly, which means Charmander stores the value of Bulbasaur, because that's what I'm asking for. Pikachu here is getting the memory address of Bulbasaur. So that right here will store 400. Okay? So that's what these two results give us. Charmander will be 21 and Pikachu will be 400. Okay, so address of Bulbasaur is 1500. It's kind of a trick question. What is the value of Charmander? So watch what's happening here. I'm setting Bulbasaur equal to 21. Then Pikachu is being equal to the address of Bulbasaur. Then Charmander is being set equal to the dereferenced value of Pikachu. It means get me the value of what's stored at this memory address. Which Pikachu and Bulbasaur are both pointing to the value 21. The only difference is that Pikachu is pointing to the memory address of it. So when you ask for the value that's stored at Pikachu, it follows the memory address and gets you the value that's stored there, which is 21. If I were to put this in the example here, Bulbasaur here is 21. Pikachu is being equal to the address of Bulbasaur, just like the previous example here. Then Charmander is equal to the value of what's stored at Pikachu. So it follows this memory address at 400, says, okay, I have this memory address, I'm going to go down to here and get the value of what's stored here. It's 21. These questions you could have put into a program and run it and see what the answer is, but we'll go through the results here. So I have 3 variables, 2 integers, and a pointer to an integer. I'm going to set the pointer to an integer equal to the memory address of what's stored at A. And then I'm going to change the value of what P1 is pointing to 5. I'm going to change the P1 variable to point to the memory address of B. And then I'm going to change the value of P1 again to 10. So I had P1 point to 2 different memory addresses. I reassigned the memory address that I was pointing to. And then I change the value stored at that memory address. And then look what I'm printing out. I'm printing out the variables a and b here. So if I run this, what you'll actually see is that a and b print out 5 and 10, even though they start at the values of 10 and 20. And that's because when I change the value of what P1 is pointing to here, that's changing the value of A, because it's pointing to the memory address of A here. Okay, so this will print out 5 and 10. Okay, questions on this? All right, last one. I have an array here, and this is actually from the book for pointer arithmetic, with 5 numbers in it, 1, 2, 3, 4, 5. I have a pointer to P1, called P1, and I'm pointing to the memory address of the second element in this array, or sorry, the third element, index 2, so it's pointing at the value 3. Then I'm printing out what's stored at that memory address here. What's stored at the memory address of this value is 3 here. So this one here just gets me back the number 3. Then we do this thing right here. Now this is kind of purposely written that you can get the right answer either way. However, what we're doing here is we're adding the number 2 to a pointer variable, and this is what's called pointer arithmetic. It's a little bit different than regular math. For instance, I'm going to get the value 5 here, that's my answer. But if I change this homework a little bit, when you see addition being done on a pointer and directly a pointer, it's not adding a number to that memory address. What it's actually doing is jumping that memory address a certain amount. So in this case here, when I add 2 to P1, it's saying, hey, go forward 2 spaces in memory and tell me what's at that location. So in this case, it'll actually give me back 10 here, when it'll print out 3 and then 10. Let me show you what that means on the spreadsheet here. So I have an array here. I'm going to say I'm going to have an array A, and it has the values A of 0, 0, 0, 1, 2, 3, 4, 5. Maybe just 1, 2, 3, 4, 5. And I'm going to do this 1, 3, 5, 7, 9. Okay, this is my array of memory. I'm going to have a pointer. I'm going to call it a Pikachu pointer. 0x03. Okay. If I take my Pikachu, so what is Pikachu pointing at right now? It's pointing at this memory location here. So if I ask for a dereference of Pikachu, what is my value here? 1. It'll be 1 here because that's what it's pointing at. Pikachu here, remember, it's storing the memory address 3, so just look on the left here, it's storing this value. Pikachu by itself is storing the value 0x03. If I take Pikachu and add 2 to it, this is actually a, let me correct my example here a little bit just to make it more correct here. I was trying to simplify it, but it actually makes it incorrect a little bit. Plus my memory addresses are not correct. This would be 20, even though this is not correct math. It's supposed to be hexadecimal. I'm going to fix up my memory addresses here. Pikachu is not pointing at 04. I think a lot of people would expect it to be pointing at 0x06. Right, because I'm adding 2 to that. It looks like I'm adding 2 to the memory address. Pointers are, what's that?
X12.
It would be pointing at x12, yeah. Pointers are special. You can't just add numbers to pointers. In fact, when you try to do an addition operation to a pointer, what it's actually going to do is jump down one of these rows instead. When you do pointer arithmetic, when you do something like this, where you add a number to a pointer, it's actually going to take what it's pointing at and jump it down that many slots. So it's actually going to point it at the next 2 down from where it's currently pointing. So it's actually going to point at 0, 12. Okay. So if I take Pikachu, that's 10. That's what it would point at. This is special. This is so pointer arithmetic is actually really, really important for game developers because when you're working with a game, it's not all just like fun, like, hey, let's make explosions and let's make like heroes in Overwatch and let's make like cool UI and all these neat abilities and like play games all day. Gameplay programmers oftentimes have to work with the concepts of dealing with memory in games. And think of a save game, for instance. Think of like, hey, I'm writing a game and I want to write a save game system, right? I want to save out my RPG character. I'm playing Skyrim or whatever. And in Skyrim or Fallout, I want to save out my character and all of the items and all of the loadout that I have to disk. I hit quick save. What actually happens when you hit save in like a Fallout game or Skyrim, right? Like, have you guys ever thought about what happens when you hit save in an RPG or like a single player game?
Well, it can't like just save all of the stuff, so it kind of just like takes an image kind of like everything and then just stores it. Like that's how I think of it. It's like it kind of just
Stores that code.
Yeah, it just stores whatever's like the information that the user is like has put in through like whatever they've been doing.
So logically, yeah, you don't want to save the state of everything. Sometimes you do.
Yeah.
Sometimes you want to save literally the state of everything, right? Sometimes depending on the village or your house, for instance, like what you have in your house, it'll save that. I'm more talking about like, what does that file on disk look like? Have you guys ever opened up like a save game file? You can't like open up in a text editor, right? Like you can't just like edit it by hand. So there's like hacks and stuff you can download that lets you modify. What's that?
Minerva for Flash games.
Lets you like modify the save games.
Yeah.
But have you guys ever thought about like how you get that stuff on the disk?
Yep.
So a lot of that stuff has to deal with how you manage pointers and use pointer arithmetic. So if you imagine the high level concept of saving something to disk is that you have these data structures in C++. You have this thing that represents a Pokemon or a move, let's say. And a Pokemon you guys did in your homework has like a name and stats on attacks and defense and special attack, special defense. And you want to put that stuff onto a file somewhere. So the way that you do it is that you imagine that you have this file, and the only way I can really do it is through Paint, the marvelous of Paint, is that you have a file, and this is all blank. This is my save game file. And the very first thing you do, this is super naive, and this is not 100% accurate, but it's close enough. I want to save the Pokemon's HP, right? So what you do is you say, hey, I need a block of space on my hard drive to store a number, okay? So you say, okay, cool. I'm going to write a number right here. I'm going to write a number that's like his HP, which is like 30 here, okay? What you do is that you have this pointer that was pointing to the beginning of your block of memory, and then you said, okay, I need this block of memory, so I'm going to move it over here now, and that's where I'm going to start writing the next thing that I want to store, maybe his speed. So I need something that stores his speed. So I do that. And then I'm going to write his speed in there, I don't know, 4. And what you do is you advance this pointer, say, cool, well, I had enough memory to store that, so let me move that so I can store the next thing in memory. And some of these things are not as big as others. Like a string, for instance, might be this long. Right? Maybe he has the name Bulbasaur. Right? And then you advance the pointer again. And you continue to do this, writing out the individual elements that you have on disk. When you go to load that save game, what you do is you open that file up in C++. There's routines in C++ to let you basically point to a file and say, okay, I want to read from this file. And it says, cool, here's the file. I opened it for you. And here's the pointer back to where the beginning of the file is. You say, all right, I need to read my memory now, which means you have to understand the order in which your save game is written out. So you say, okay, I always know that I wrote my HP out first for every Pokemon, so I'm going to read my HP, and I'm going to advance my pointer to the next thing. So when I read that back out, I know that the next thing, which was, I think I said speed, I'll read that out, and that's going to go into my speed for my Pokemon. I'll advance my pointer, and then now I need to know how much to read for my string. I'm going to read my string. Strings are a little bit complicated, actually, because oftentimes when you write a string, what you do is you don't just write the string. The first thing you actually write is this little block. You have a tiny little section right here, which indicates how long the string is. 1, 2, 3, 4, 5, 6, 7, 8, 9. You have this little block of memory. Oops. That says there's 9. There's 9 characters in my string. You say, okay, first off, I'm going to read how many characters are in my name. I say, oh, it looks like there's 9 characters here. Cool, I got that. Okay, I'm going to get ready. I'm going to read one character at a time. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I read all the characters that I know are there. Okay, I read my save game, and I'm done. And then you advance that pointer back. Okay, you keep on going through the memory, reading the bits of information as you store them. It's a really rudimentary basics of how you store and load files, but this concept is pretty much used for like our editor as well, for like saving and restoring assets that people have been editing. Really simple save game systems use this as well. So like you want to save a game locally on a disk, you can do this. And then sometimes you can encrypt it. Sometimes you can put a version in the front of it so you know that, hey, this order is really important, that I store HP, then speed, then the name. However, if later I want to store defense as well, and I forgot to include that, I can't just use my old save game files, right? You guys ever know, like, sometimes save game files are not compatible with like older versions? Well, that's because like in my code, I'm expecting to read HP, speed, and then defense, and then name. However, this old save game file doesn't have a defense number here in between these two. It has the characters for how many characters are in my string. So that's why those things are a little bit incompatible. I could write a patcher that lets me read that value in if I know that this version's old. But all that necessitates me to have a version, this is a very common thing. So you have this whole thing here, and in the front here, you will put a version number. Like this might be version 1. And you read that first. Always, always, always read that first, no matter what. But that's why pointer arithmetic is really important, because in order to navigate the memory of writing and reading this file, you need to be able to move this pointer around in memory. Okay? All right. I know that there's a lot of stuff there that we talked about. I would love to spend more time on this. I could spend like several classes talking about save games and loading them, and like file structures on disk, and how to write something like, I don't know, like an asset system or a level editor that you can load. But this is all would be using pointers to help you with that. So, okay. All right, and that's the last of it. Questions? Okay. I think I need to give you guys a break before I go on to the lab. So, give you guys a